Imagine a force that governs everything in the universe, a superforce that controls all matter and energy. Intriguing, isn't it? This idea might sound straight out of a science fiction novel, but it's more than just a fanciful concept. The idea of a superforce has been a topic of fascination not just in modern physics but also throughout history and across cultures. Ancient civilizations often believed in a unifying principle or force that governed the cosmos. From the ancient Greeks who believed in logos, the divine reason implicit in the cosmos, to the Chinese concept of qi or qi, the vital energy that flows through all things, the idea of a superforce is as old as civilization itself. In modern times, this idea has found a home in the realm of theoretical physics. Here it's known as the unified field theory, or the theory of everything. This theory seeks to unify all the fundamental forces of nature into a single framework. The four fundamental forces, gravity, electromagnetism, strong nuclear force, and weak nuclear force, govern the behavior of all matter and energy in the universe. If we could find a way to unify these forces, we would essentially be dealing with a superforce. However, the quest for this superforce is not without its challenges. It's a complex puzzle that scientists have been trying to solve for decades, if not centuries. Each piece of the puzzle, each fundamental force, has its own unique characteristics and behaviors. Finding a common thread that ties them all together is no easy task. Yet despite these challenges, the search for a superforce continues, driven by our insatiable curiosity and our innate desire to understand the universe and our place in it. The concept of a superforce, therefore, is not just about physics. It's also about us, our quest for knowledge, our thirst for understanding, and our ongoing journey of discovery. The concept of a superforce has been a cornerstone of many scientific and philosophical debates, and as we delve deeper into the mysteries of the universe, who knows what fascinating discoveries await us. After all, the universe is a grand, intricate tapestry, and we have only just begun to unravel its threads. To grasp this concept, we must first understand the four fundamental forces in physics. These forces are the pillars that uphold the universe as we know it, governing the behavior of every particle and celestial body. First, there's gravity, the most familiar of the lot. It's the force that keeps us grounded, quite literally. It's responsible for the Earth's orbit around the sun, and for the apple that fell on Newton's head. Despite being the weakest of the four forces, gravity has the longest reach, extending its influence across boundless galaxies. Next, we have electromagnetism. This force operates between charged particles, and it's what makes magnets stick to your fridge and your hair stand on end when you rub a balloon against it. Electromagnetism is immensely stronger than gravity and is responsible for holding electrons in their orbits around atomic nuclei. Then comes the strong nuclear force. Despite its name, it's not about being physically robust. It's about holding the nucleus of an atom together. Without this force, every atom's nucleus would disintegrate due to the repulsive force between protons. The strong nuclear force is about 100 times stronger than electromagnetism, but its influence is limited to the minuscule scale of atomic nuclei. Finally, we encounter the weak nuclear force. This force is responsible for radioactive decay and certain types of nuclear reactions. Like its strong counterpart, the weak force only operates at tiny atomic distances. These four forces are the fundamental mechanisms that govern the dance of particles, from the smallest quarks to the largest galaxies. They are the symphony that creates the cosmic music we are a part of. Yet the intriguing part is that these forces, although different, might be interconnected in ways we are still striving to comprehend. This is the quest for unification, the search for a single theoretical framework that can explain all these forces. This pursuit has led us to consider ideas as radical as string theory and as elusive as dark energy, but that's a tale for another time. These forces, although different, might be interconnected in ways we are still striving to comprehend. Scientists have been on a relentless quest for a grand unified theory. This is a pursuit that has been at the heart of theoretical physics for decades. The grand unified theory, or GUT for short, seeks to merge two of the four fundamental forces that govern our universe: electromagnetism and the weak nuclear force. Imagine, if you will, the universe as a giant jigsaw puzzle. Each piece represents a force, a particle, a rule that governs our reality. Now consider the pieces that represent electromagnetism and the weak nuclear force. These two forces may seem distinct, but they are actually two sides of the same coin. Electromagnetism, the force that lights up our cities and powers our technology, and the weak nuclear force responsible for radioactive decay were once thought to be completely separate. However, in the high-energy conditions of the early universe, these two forces were one and the same, a unified force that we now call the electro-weak force. A grand unified theory aims to bring us back to that primordial state, to a time when the universe was simpler, when forces weren't so forcefully divided. It's a quest to find the common thread that weaves these forces together, to uncover the underlying simplicity of our complex universe. But what would a successful gut mean for us? It would be a monumental leap in our understanding of the cosmos. It could explain why we have more matter than antimatter, could provide insight into the nature of dark matter, and might even pave the way for new technologies. Yet the quest for a grand unified theory is not without its challenges. We are trying to make sense of the universe at its most fundamental level, and the universe isn't always willing to give up its secrets easily. We're pushing the boundaries of our knowledge, venturing into uncharted territory. But isn't that what makes science so exciting? A successful gut could radically shift our understanding of the universe. It's a quest that continues, a journey that we are all a part of. As we delve deeper into the mysteries of the universe, who knows what we might discover? One promising candidate for a unified theory is string theory. A concept that has been the subject of intense study and debate for decades, string theory fundamentally differs from the standard model of particle physics. Instead of treating particles as zero-dimensional points, string theory proposes that these fundamental entities are actually one-dimensional strings. These strings, unimaginably tiny, vibrate at different frequencies, and it's these vibrations that give rise to the properties we associate with various particles. Picture a violin string. Just as it can vibrate to produce different musical notes, these fundamental strings of the universe vibrate to produce different particles. This is where the beauty of string theory lies. It provides a holistic framework that could potentially unify all fundamental forces, from gravity to electromagnetism, under one mathematical umbrella. But string theory is not alone in the quest to go beyond traditional particle physics. Other theories, such as loop quantum gravity, also offer alternative perspectives. Loop quantum gravity, for instance, suggests that space-time itself is quantized, composed of finite loops and nodes. This gives us a different way to approach quantum gravity, without the need for extra dimensions as in string theory. There's also M theory, a proposed mother of all theories that unifies all consistent versions of string theory. This theory suggests that our universe may be one of many in a vast multiverse, each with different physical laws. And let's not forget about quantum field theory and curved space-time, a theory that combines quantum mechanics and general relativity to understand how particles behave in the presence of gravity. This theory has been instrumental in predicting phenomena like Hawking radiation from black holes. These theoretical approaches, each unique and fascinating, represent our continued attempts to delve deeper into the fundamental nature of the universe. They reflect our insatiable curiosity, our relentless pursuit of knowledge, and our collective aspiration to uncover the ultimate truth about our universe. String theory, although not universally accepted, offers a tantalizing glimpse into the potential unity of fundamental forces. And as we continue to explore and question, who knows what other theories might emerge from the depths of the cosmic ocean? Among the cosmic forces, dark energy stands as a profound mystery. This elusive entity, first proposed in the late 20th century, is believed to account for nearly 70% of the universe's energy. But what is it exactly? Well, in simple terms, it's an energy source that permeates all of space, driving the acceleration of the universe's expansion. Let's delve a little deeper. When astronomers observed distant supernovae, they expected to see these stars slowing down. Instead, they found the opposite. The universe wasn't just expanding, it was expanding at an accelerating rate. This unexpected discovery led scientists to posit the existence of dark energy, an unseen force opposing gravity, and causing this accelerated expansion. Dark energy's mysterious nature extends to its impact on the cosmic structure. We know it's there because of its effects on the universe's large-scale structure. It's a bit like wind. You can't see it, but you can see its impact on the world around you. Dark energy influences the distribution of galaxies, the shape of the universe, and even the fate of the cosmos itself. Yet despite its ubiquity, dark energy remains a puzzle. Theories abound, from the cosmological constant, a value Albert Einstein initially proposed then later dismissed, to quintessence, a dynamic energy field that changes over time. Some theories even suggest that dark energy is a symptom of gravity behaving differently on cosmic scales. But here's the kicker. Understanding dark energy could be a game changer. Could it be the missing piece in the puzzle of the superforce? Could it help us unify the fundamental forces of the universe? It's a tantalizing possibility. After all, dark energy, this mysterious force causing the cosmos to speed apart, could hold the key to understanding the very nature of our universe. The exploration of dark energy could potentially unlock secrets about the universe and the superforce. Scene script. Gravity, the most familiar force, has a dominant role in the universe. Gravity. It's the force that keeps our feet firmly planted on the ground, the moon circling our planet, and our planet swirling around the sun. But its reach extends far beyond our immediate surroundings. Gravity is the key player on the cosmic stage, governing the motion and formation of stars, galaxies, and the vast cosmic web that structures the universe itself. In this vast cosmic theater, gravity is the lead actor, its effects rippling across billions of light years. Stars, galaxies, and even clusters of galaxies are all bound together by the invisible threads of gravity, forming a complex cosmic web that spans the observable universe. This web is not static, but rather constantly shifting and evolving under the influence of gravitational forces. Gravity's influence is not just local, it's universal. It affects the motion of everything in the universe, from the tiniest particles to the largest galaxy clusters. But gravity also shapes the universe on a far grander scale. It's responsible for the large-scale structure of the universe, the distribution of galaxies, and the formation of cosmic structures. But despite its dominance, gravity remains the least understood of the four fundamental forces of physics. It's the only force that has not been incorporated into the quantum mechanical framework that describes the other three forces. This gap in our understanding is one of the biggest unsolved problems in physics today, and it's a key motivation behind the quest for a unified theory of everything. Gravity is also unique in that it is always attractive, never repulsive. This means that it has a cumulative effect over large distances, becoming the dominant force on cosmic scales. This is why, despite being the weakest of the four fundamental forces, gravity rules the universe. As we delve deeper into the mysteries of the universe, we realize that gravity, in its silent pull, might hold clues to the superforce we are seeking. Its dominance in shaping the universe and its unique properties make it a crucial piece of the cosmic puzzle. And as we continue to explore and understand gravity, we might just uncover the secrets of the universe itself. Gravity, in its silent pull, might hold clues to the superforce we are seeking. Unifying all fundamental forces into a single superforce is a daunting task. But why is it such a mountainous challenge? It's because the world of physics as we know it is a complex labyrinth of theories, equations, and concepts. Firstly, the fundamental forces behave differently on different scales. Gravity, for instance, is the dominant force on a cosmic level, but it's virtually negligible at the atomic scale. Conversely, the strong nuclear force holds atomic nuclei together, but it doesn't extend to larger distances. Unifying such disparate forces into a single mathematical framework is like trying to solve a puzzle where the pieces come from different sets. Secondly, quantum mechanics and general relativity, two of our best physical theories, are at odds with each other. Quantum mechanics is superb at explaining the world of the very small, while general relativity beautifully describes the universe on a grand scale. But when they're forced to interact, such as in black holes or the Big Bang, they clash, leading to nonsensical answers. This discord presents a significant hurdle in our quest for a superforce. Furthermore, there's the elephant in the room, dark matter and dark energy. These mysterious entities make up a whopping 95% of the universe, yet we know so little about them. How can we talk about a superforce when we're still grappling with understanding most of the universe? Finally, our understanding of the universe is limited by what we can observe. There could be forces or particles out there that we haven't detected yet, simply because our current technology isn't advanced enough, or because they exist in realms beyond our reach. In a nutshell, the search for a superforce is like navigating an intricate maze, with each turn revealing a new challenge. But it's these very challenges that make the journey exciting. Each hurdle overcome, each mystery unraveled, brings us one step closer to a deeper understanding of the universe. Despite these challenges, the quest for a superforce continues, fueling the progress of science. The idea of a superforce governing the universe continues to intrigue scientists and philosophers alike. This journey took us from the fundamental forces in physics, through the ambitious quest for a grand unified theory, and beyond traditional particle physics with string theory. We've explored the enigma of dark energy and the dominance of gravity on cosmic scales. We've also acknowledged the limitations and challenges in this search, highlighting the complexities of understanding and unifying all fundamental forces. The philosophical and theological implications of such a superforce have been touched upon, as well as the skepticism within the scientific community. We've journeyed to the boundaries of our observable universe and peeked into the possibility of forces existing in unobservable realms. Emerging theories and research continue to push this fascinating field forward. So I encourage you all to explore further and stay informed about developments in the field of theoretical physics. Who knows, the discovery of a superforce may be just around the corner. Until then, keep questioning, keep exploring.